Okay. So let us come back to the concept of channel. Okay. So what do we mean by channel? That's something we want to discuss. We have already discussed about different forms of channels, like let's say if just I list them. One is the wireless channel, which is the air media that we know. Another is twisted pair, okay, which is means being used for our telephony transmission. You might be aware of this. So third is coaxial cable. This is being mostly used for broadcasting television signal. This is also something you have seen already. The fourth part may be optical fiber. This is the latest one, which supports huge amount of bandwidth, if you are aware. So the fifth might be satellite channel. So on and so forth. So there are multiple channels that are communication channels, especially that are available. Through all of them, actually the mode of transmission is its electromagnetic wave. Okay. So for wireless, it's not guided. Okay. So it's just radiated electromagnetic wave. Whereas for all other cases, it's actually guided electromagnetic waves. Optical fiber, it's still electromagnetic wave, but at the visible optical region. Okay. Or let's say the frequency is such that it is called the optical electromagnetic wave. Okay. And so all of them are mostly electromagnetic wave. Through that only signal propagates through a channel, whichever channel we pick. Now what channel can do? Let's start discussing about these things. The first thing which channel can do, let me list out first what are the things that channel does, and then we'll discuss about them. So the first thing is channel can introduce noise. This is probably the most important part of communication. What is noise and how noise affects. So communication engineer must know very well about noise, and that's probably the biggest enemy of our means our threat. Okay. So second part is distortion, and the third part is interference. Let's talk about them one by one. So what is noise? Noise is again what we are doing. We are trying to transmit an electrical signal which is being converted into electromagnetic wave, and in the channel what might happen due to different reason. Okay. So there might be this random electromagnetic waves which can be added to this particular transmitted signal. So what we generally say, channel is, if we say we characterize the channel as a additive channel. Okay. What do we mean by additive channel? As if it's like a simple adder of signal. So whichever signal gets means we put as input to this channel, if there are multiple such signals, it will just add up those signals. So suppose I have a signal F1t. Okay. So I'm just writing the voltage of that signal, and this is the variation with respect to time, that this is called the F1t, function of t. So suppose this is my signal that has been put into the channel, and then if there is another signal that is also being kept or put inside the channel, let's say F2t. Okay. So what the channel will do? Channel will simply add these things. So at every time instance, it will take this voltage and this voltage, it will add and put things. Okay. So every time instance, if you pointwise add these two signal, you will get a composite signal, which is a typical criteria of a additive channel. If the channel is additive, we generally say the channel is linear. Okay. But there are non-linear channel also, where simple addition does not work. It might be maybe f1t plus f2t whole square. So it might start creating all the square, cube terms. So those are nonlinear channel. But here we are just saying our channel is, let's say, that's one characteristics of the channel, that it is a simple additive channel. That means any signal, number of signals present in the channel, they will be just means amplitude added, or in terms of electromagnetic wave you will see that similar effect. So that whenever you convert that composite electromagnetic wave into a signal, it will just be addition of those two signals. Now what's noise? Noise is inside the channel there are electromagnetic wave which is being generated. It might be due to lightning, it might be due to spurious radiation coming from outer space, it might be the radiation, other forms of radiation that are generated on earth and being reflected back from the ionosphere, whatever it is. There might be multiple random signals which we have no idea, because it's generated from elsewhere, we have no idea, and this might be generated without our control, and this might means be as input in the channel. We cannot help it because we are using this channel, so there will be some spurious signals always being generated or created inside that particular channel. If it is wireless, I have talked about all those examples like electromagnetic radiation from outside and all those things. Even for wired also, it cannot be fully shielded, so always from outside some electromagnetic radiation can leak into the channel, and it can co-propagate along with my signal. And then definitely if the channel is additive or linear, we should say, then that signal will be added with my signal. This random signal which I have no hand in generating, I have no control in it, it will be anyway generated and added to my signal, that's called noise. So if you see, therefore the noise is just another random signal. I am calling it random because I have no control on it. It can be generated without my knowledge and without my influence. So that is why it is actually a random source of information for me. So this particular is always inevitable, it will be present in the channel and it will be added. So when we say noise, you might be saying, okay, is noise just being added at the channel? Precisely not. Noise also can be added at the transmitter, because transmitter also will be having some hardware. In the hardware you will have, let's say, all components, transistor, some resistor and all other components. Just take the simplest of component, let's say resistor. Whenever my signal, it has to be transmitted, so it has to be processed through this hardware, so it must be passing through a particular resistor. And inside the resistor, what will happen, even if I suppose I transmit this signal or I pass this signal through the resistor, it will not be completely, suppose I have a resistor through which I am passing this signal, this f1t, whatever it is. Okay. Now at the output, what will happen? See, through the resistor I will be actually creating this voltage, time varying voltage, or this f1 equivalent to f1t, and accordingly the current will be flowing. But what will happen, inside the resistor there are multiple carrier electrons. They are also doing Brownian motion. Due to the Brownian motion, they will have random movement. So what will happen, on top of this there will be some random signal which will be added, and my output signal will look like this. So it will almost follow the pattern of my f1t, original f1t, but it will also have this small things added which is just being generated due to the Brownian motion of the carrier electrons. Okay. So this will be true for any hardware, any electronic device we put. So in transmission or transmitter there will be electronics which will generate this noise. In receiver also there will be hardware which will also generate this noise. So noise is not just, it is one of the my channel is one of the source as we have discussed, but noise will also be generated at the receiver, noise can also be generated at the source where from I am actually starting my transmission. So everywhere there can be noise, but channel is one of the source of noise. So that is why whenever we are characterizing channel, we need to understand also what should be the noise, or what should be how much noise will be added, what's the characteristics of that noise and all those things. Though we have talked about it is a random signal. I have no knowledge about it. How it will vary with time, I have no knowledge about it. It's not my generated message, so I don't know exactly how it will be generated. Okay. So the pattern at which it will be varying, that will be completely random. That's true. Okay. But I have to still get some characteristics, and that will be a major focus of this course. How do we characterize noise, and in presence of noise, how do we combat noise in the transmitter side as well as the receiver side, so that noise does not actually change my voice signal. So you have already seen, suppose my voice signal looks like this F1T, and on that F1T I start putting noise. So what will happen? The voice signal will be little bit varied, and how much it will be varied, how much I can tolerate, all those things has to be in consideration whenever I am transmitting, and possibly as much I can get rid of that, and as much pure F1T I can generate at the receiver, that much faithful the communication will be, or the communication will have that much clarity. Okay. Next is distortion. What do we mean by distortion? Let's try to think about that. Whenever we talk about a channel, generally the channel, any form of channel you see, the channel will have some low pass effect. So that means it can carry frequency up to some value. Beyond that, it will not be able to carry those frequency. Those frequency will be suppressed. So that's the low pass characteristic. So channel transfer function, if we just see, it will almost look like this. So up to some cutoff frequency, probably it will be almost carrying that signal, but after that it will be hugely attenuated. Okay. So if this happens, suppose our signal has multiple component, different frequency component, then what will happen? Some of the frequency component will be actually equivalently carried, but some of the frequency component might get little bit suppressed. What's the effect of that? You all know about low pass filtering, whoever has read little bit on signals and systems. So let's say I am transmitting this kind of signal. Okay. So this is voltage level, let's say 0, this is voltage level, let's say 5 volt. Okay. So I am trying to transmit this kind of signal. Now this is where we will be later on seeing also that this is where at this edge or this edge or this edge, all those high frequency components are there, because at a negligible time the voltage level is varying hugely. So that actually calls for very higher frequency, because in a very small amount of time huge amount of voltage change or amplitude change is being happening. So high voltage, high frequency components are involved in that part. This is the part where signal remains almost constant over time, so probably not much of high frequency components are there. So what happens in a low pass filter, those high frequency component will be suppressed. So basically as an effect, this particular part will be smoothened. It cannot really sharply jump because the high frequency component will be suppressed. So at the output of the channel, if we take the channel as low pass filter, what will happen? It will look like this, almost like charging and discharging of a capacitor. Okay. Because after all that works as a low pass filter. So this is what will be happening. Basically you can see I am trying to transmit something. Because of the low pass nature of the channel, the signal is getting little bit distorted. Okay. Not only that, as you go along a huge distance, there will be also loss associated with the channel, because channel might have absorption loss, so it will take away some of the energy of the electromagnetic wave. It might be due to air, means radiation in the air, it might go in different directions. So at the antenna probably only a portion of that radiated energy will be linked. So what will happen if I transmit some amount of energy, at the end this will really become very small. So something like this. So my 1 now will come close to 0 because the energy level is getting depleted, and also the signal form is getting little bit distorted. So this is actually the part of distortion that we generally see in the channel due to the low pass effect, due to the absorption and attenuation of the channel. Okay. There are other distortion we were talking about. that we are just assuming, we have been assuming that the probably channel is linear. Okay. In a linear channel, forget about the noise. If no other signals are present, my signal only is being carried out. If the noise is sufficiently small, then my signal will be faithfully, only that signal will be carried out through the channel. But what might happen if the channel is no longer linear? Then suppose the channel output, we say Wt, suppose I give input as F1t and the channel is not a linear one. So if it was linear, maybe there is a constant term C into F1t it will be. The C is the attenuation. So that will attenuate from here to here, the signal level. Okay. So let us say C is 0.1 or 0.01 depending on how far your receiver is, what kind of absorption or loss or attenuation the particular channel has. So depending on that, the signal strength will be little lesser, but the signal quality will remain the same. But instead of that, if the channel has non-linearity, then what will happen? OT will be some C1, let us say another constant, into F1t whole square. Okay. It might be if it is just pure quadratic, or it might be means quadratic with all other terms, let us say C1 F1t whole square plus C2 F1t. So that is the channel function, let us say, and C3. If it is like this, then what is happening? The OT is not proportional to, earlier when it was linear, it was proportional to F1t. Now no longer it is proportional to F1t. So there will be added distortion, okay, due to this squaring, or if you have even higher order non-linearity in the channels, let us say cube or to the power 4 and all those things, then there will be added distortion. The signal will look like different because there will be a square term added by some other linear term and some constant term. So there will be some distortion due to that non-linearity of the channel. So there are multiple ways that channel can give you distortion. One is the low pass filtering effect. The second is the distortion itself, which can also keep the channel non-linear. Okay. Due to that non-linearity, only distortion is coming up, and then you have some attenuation, which significantly reduces the energy level of the signal. So that's the second part of our discussion, what channel can do. The third part is, which is also inevitable, which is called interference. So this interference comes when multiple signals are being transmitted simultaneously over the same channel. Even if we take care, very nice care that we have discussed about modulation, there will be still some spurious portion of the other signal which comes inside the band of our desired signal, and that will create again some amount of impurity into your signal, because that is a different signal which is now getting superimposed with your signal, that will contaminate your signal. The pattern of your signal which carries the information actually will not be sustained if that happens. So these are the three sources that can contaminate within your channel. So you have to be very careful about noise, of course. You have to be very careful about distortion, and that is why we have discussed about the channel. So you need to characterize the channel, you need to know exactly what kind of noise it gives, what are the if it is random, what are the stochastic nature of those noise. Then you need to also know what kind of distortion the channel gives. If it has nonlinearity, what kind of nonlinearity, what are the coefficients of those nonlinearity. So all those things has to be known. If it has a low pass filtering effect, what's the characteristics of that low pass filter, due to that what kind of distortion the signal will get, and also if it has attenuation, how much attenuation it gives. So all these things has to be known, and then you have to also know if there are other signals which are present, what's the effect of the interference. These three things should be very clear whenever you are transmitting, because eventually what will happen, as we have discussed, that any signal you transmit, so we had this transmitter, we had this channel, and we had this receiver. So this is actually the transmitted signal. So transmitted signal may be very nice, but what might happen, due to the channel, I am just taking out the interference and as well as nonlinearity of the channel. So even if we take out that, what will happen after passing it through a channel, this particular signal will become like this. It will be something like this, and on top of that there will be noise added randomly. So this is actually going to be your received signal, and that is why we said transmitted signal and received signal might not look alike, they might be completely different. So this is one fact we have to live with, and this is the fact that we need to deal with mostly in communication, that probably our channel will give some distortion, some amount of noise interference to the signal, and my received signal will not be completely faithful representation of the transmitted signal. So therefore what I need to do, first of all we need to characterize this, how much distortion, how much noise will be added, and we need to know how to combat this and to get back my original signal, because that's the whole purpose of communication at the receiver. So this is something we'll be trying to do in our communication. Okay. So next what we'll start we'll probably do it in the next section of our or next part of next half of our course. We'll talk about modulation little bit. So I'm just here just going through all the models of communication that are required, why they are required, and what kind of things, very briefly, without giving any details of it, very briefly making you familiarize with these concepts. Once we get some hold of this and we know actually what are the things we need to consider, then we'll actually go into details of each of them. So our next target is that modulation. We have already discussed very lightly what modulation is. Now we'll try to characterize those modulation techniques. What are the different modulation techniques that we have? How do we actually characterize them? So those things we'll discuss a little bit. Okay. So in modulation, especially in analog communication, we'll be talking about two forms of modulation. One is called continuous wave or CW modulation, and the other one is pulse modulation. Okay. These are the two most common version of modulation. One is called continuous wave modulation, the other one is pulse modulation. So basically whatever example we have given, that modulating the amplitude of a carrier or modulating the frequency of the carrier, that's actually called the continuous wave modulation. That means the carrier wave is continuous. Okay, that means continuous means it's actually in time. If we just go everywhere in time, any time instance you define, there is some it has a continuity over the time, and there is some amount of amplitude you will be getting always. Okay, so that's actually the continuous wave modulation. In pulse modulation, what we do, we actually take a signal, and the signal looks like this. It's periodic pulse. So it is no longer a continuous kind of signal. It is just defined over this small duration. Rest of the duration it has nothing. Again, for a small duration it is defined, and that's called the pulse. And this is actually a pulse train, a periodic pulse that goes around. So if somehow I can put my information inside this pulse. Okay. Now what are the criteria that has? Each of these pulses have few things. One is the width of the pulse. Okay. Like for the sinusoidal, we were trying to see what are the characteristics or what are the basic features that the sinusoidal have, or what are the main things that sinusoidal have which we can modulate, where we can introduce our signal. Okay. Here also we are almost looking like that. So we are trying to see what are the characteristics, basic features of this pulse. So one is this pulse width, another one is this pulse amplitude. Okay. Like the sinusoidal there was an amplitude, here pulse also has some amplitude, pulse have some width. Okay. So this will be in time, how much millisecond or microsecond is the pulse width. So that's another thing. And then if the pulse is periodic, I can also vary the location of the pulse. So I can slightly deviate the location of the pulse. So that's called the position of the pulse. That's also another variability that I can get. So position, width, and amplitude. And for modulation, I can use all three of them. Suppose I need to transmit this signal, let's say this signal, okay, and I have pulse train which are coming like this. Okay. So in pulse amplitude modulation, what we'll do, we'll actually borrow the amplitude and put it at every time instance to this. So basically the amplitude of this pulse will be modulated or will be mimicking the shape of this signal. So here the pulse amplitude will be this, here it will be a little bit higher, here it will be something like this, so that if you just connect the tip of those pulses, you will see this signal being formed. Okay. So that's actually called the pulse amplitude modulation. So the pulse amplitude is now being modulated according to your message signal, which is let's say F1t. Okay. The second part is that I have again this signal, right, and I have this pulse. What I do is I actually modulate the width accordingly, almost like frequency. So as the, and what my mechanism of modulating this width is, as I increase the amplitude or as I see an increase in the signal amplitude, I actually either increase or decrease the width of this pulse. Okay. So basically here there will be so there should be a minimal width which is referred to the minimal part of the signal. Okay. And accordingly I will be varying the width from here to here. There will be some scaling of varying the width. So let's say this is the minimal part. So here the pulse should be of minimal width, and then whenever it increases, here it is increases slightly. So the pulse should be little bit more. Here it is increased slightly more, so here the pulse width should be more. The period or the center of this pulse should have the same frequency as this. Whatever time it has, this time the center of this pulse will have the same time, but the width of the pulse is now getting modulated according to the message signal. So basically what is happening, the pulse is being carried now, and there is a characteristics of that pulse which gives us indication about the signal. If you just look through the width of those pulse train, you will get a view of the signal, how it should vary over time. Same thing can be done over the pulse position. So for pulse position, what we do, we have again a signal, and let's say these are the pulses, periodic pulse with same repetition interval, and then when we modulate the position, now again what we do, we actually vary the position of the pulse. So from here center, I can actually take the pulse here and there, and how much I push the pulse on the right or left side, that depends on what is the signal strength. So let's say I always, if the signal is positive, I go into this direction, and let's say my rule is if the signal is anytime hitting negative, then it goes in this direction. And we say the maximum signal level, let's say this, and suppose that signal 0 is over here, okay, and the minimum signal level, which is this, that's the maximum right shift or left shift of the pulse. So let's say that we have decided up to this. So here the pulse will be maximum let us say negative, it will be left shifted. So, it should go maximum left shifted. So, that is the center of the pulse, left shifted. This pulse, because it is little bit less negative, so it should be less shifted. So, this should be more closer to the center of the pulse, and so on. Which one? Now at this 0 level there is nothing, but this is again, let us say this part is positive, so it should be positive shifted. So, it should be on this side, and then this is more positive, or let us say this one again, it should be positive shifted on this side. So, if you now see the pulses, they are now disturbed in position. The width remains the same, amplitude remains the same, just the position of the pulse is getting drifted, and that position or location of the pulse now gives us information about what the corresponding signal strength. So, this is another form of modulation. So, we have now dealt with continuous wave modulation. In the continuous wave, we have seen that there are two parameters that can be modulated. We have a carrier. We can modulate the amplitude. We have already demonstrated how the amplitude can be modulated. We can modulate the frequency. That also we have demonstrated that how the frequency can be modulated. We have taken there a digital or binary signal, but you can as well take this kind of signal again, but we will see the same result. Only there was abrupt variation of amplitude. Here probably gradual variation of amplitude will be happening, or gradual variation of frequency will be happening. So, we have amplitude modulation and we have then frequency modulation. But let us say whenever we talk about frequency, there is also another term called phase. So, generally any sinusoidal must be represented as a cos omega c t plus some phase theta. Okay. So, basically we have earlier said just omega c t, but there should be some initial phase also, so which is theta. So, we actually have 3 parameter, and accordingly we must have 3 modulation. One is called amplitude modulation, one is called frequency modulation and FM, which you are familiar with, and another one is called phase modulation or PM. And similarly for pulse, we have 3 information carrying things, which are pulse amplitude modulation, that is called PAM, then pulse width modulation, PWM, and then the last one is pulse position modulation, which is called PPM. So, there are 3 pulse modulation, there are 3 continuous wave modulation, which we will be dealing with later on. Right now I have just given a very brief overview of this modulation. We will try to see what the relative merit of them, how do we mathematically realize them, how do we generate them, how do we demodulate them. So, all those things should be part of this course. So, this is just a brief introduction to this part, and we will later on see how these things can be covered later on.